Hi everyone. Thank you for signing up for this tutorial. Today was a wonderful day in Belgrade. I hope that translates to the conference. Our next level, Zorana Staka. She will present you a short course on leaf tracking, counting, and inclusion in plants using artificial neural networks. And you can start.
Okay, thank you so much. So I'm gonna start sharing my screen with you. I hope you can see this. So first of all, thank you so much for organizing this conference. Congrats to all the organizers. It's like 5 days of fun and learning. So good job. I'm happy I'm happy to be part of this conference, and thank you so much for letting me present my work. Also to all the attendees, thank you so much for coming here. Let this be just like a beginning of our conversation about artificial neural networks. So because I try to condense the matter, but there's so many questions left. So today I've created a little presentation, just like some images to help me out in explaining. So please be free, because this is like a tutorial. I like to be interactive with you as much as possible, because I'm a teaching assistant. So I'm always saying to my students, like, ask me questions. That's how I know the best what you don't understand, and I'm able to explain you in more details. So as you already heard, my name is Zorana Staka. I've finished my master's degree in Belgrade at the Faculty of Electrical Engineering, and I also have 2 bachelors, one in mathematics and one in electrical engineering. So let's begin. First of all, some prerequisites for this is some Python programming language experience. It doesn't have to be too advanced, just some basic syntax to intermediate, let's say it like that, and basic understanding of neural networks, how they're operating and what they are doing actually, because we're going to focus in this tutorial on convolutional neural networks. So I'm going to go with assumption that you have some basic understanding of neural networks. The most important, one of the most important things is the data set that we're going to use and the problem that we're going to solve. Why leaf counting, tracking, and this occlusion in plants? Because among the others, this is one of the problems that is recognized worldwide, because it translates directly to the food shortage with the never decreasing population of humans. So I'm not going to go dive deep into the problem. Let's just say that biologists think it's really important to know how many leaves are there in a plant, because that translates directly to how plant is progressing. Is it good? Is it bad? How are the conditions? So it's important to biologists. So we hop there to help them. Here, the data set, we're going to work on the Arabidopsis thaliana. Why Arabidopsis thaliana? Because Arabidopsis thaliana is kind of white lab mouse in this field, and it's used almost everywhere because the genome is short and it's sequenced, and usually what works good, conditions that are good for Arabidopsis thaliana can be translated to some other plants. So the data set we're going to use is famously known as Minervini data set, and on the next slide I'm going to show you where you can get it. But this data set has these folders A1, A2, A4. It has A3, but A3 is tobacco plants, and we're not gonna do tobacco plants today. You can try out our code, maybe adding A3 folder to see how it works. So here is some important information: number of images and size of images in each of the data set. And here you can see some of the examples. And maybe the question is, what is occlusion? Occlusion is actually overlapping, like a fancy word for overlapping, and it happens a lot when with leaves, especially when you're overlapping the the other leaf of the same plant, or maybe different plants are overlapping, and you have so many cases how it can be positioned relative to each other. And you also have like self occlusion, when the leaf is like, this is leaf and it's growing something like this or like this, and you're taking image from here. So sometimes it's hard to just say, okay, the leaves are oval or circle shape, oval shape, something like that. Maybe that's just not enough. So on the next slide, we have the form. I'm gonna copy paste this form. Just give me a second. Just give me a second. Hosts and panelists. So you can here fill the form to obtain access to download link. I know you're probably asking, why don't you provide this link directly? But I know how hard it is to actually get this data. So the authors of the data, among the others, Minervini, said like, this is the way to get to the link. So this is what we're gonna do. And big thanks go to them and to the whole community that is working on segmenting and counting leaves, because this has been problem for the maybe last 10 and more years, and there are different solutions, and today I'm going to present you one of the solutions. So here you also have plant phenotyping.org data sets overview. You can also see these papers, because it's going to give you the deeper understanding of why is it important to do this, and also some methods that have been used for leaf counting and segmentation and some other things. So for the beginning, let's first see what is this convolutional neural network. I've already said, like, my assumption is that you have some basic understanding of neural networks, and I want to present you today convolutional neural networks. With LangNet and AlexNet, convolutional neural networks have gained really some attention in a community, because they tend to be really good when solving some problems with images, because it's not enough to have let's say traditional fully connected neural networks layers, because here what this convolutional neural network does is inspired by biological brain, how our brain sees things. So for example, I mean, it's a really fast process and you don't think about that, but figure out how you recognize that its face. How do you recognize that, like here, what you see on Zoom, it's a face. You see some eyes, some eyebrows, nose, lips, cheeks, maybe someone has a beard and things like that. But you are able to recognize face maybe in 99% of cases. So how your brain does that's really interesting question. So it's already like multidisciplinary field. What was figured out is that the spatial structure of pixels is really important. So it's important that the pixel has certain neighbors. So this convolution operation, we're gonna look into this convolution operation especially, it's concerned with that spatial structure of pixels. So that's like, it's inspired, that's the most important. It's inspired by biological brain, and it takes care of spatial structure of pixels. Here you can see one of the, let's say, small, simple convolutional neural networks, where it's recognizing handwritten digits and letters. And I'm gonna reference this image later, because I'm gonna need it for explaining. Okay, let's start coding. So this is where you can get your data. You should get link soon, relatively soon, but the data is it's a little bit bigger, I think. Yeah, it's bigger. Sorry, some time passed since I downloaded. Okay, so we're gonna use Google Colab. Why Google Colab? Because it has some performances that's gonna be good for us, but I would advise you to run it maybe on Azure, because I did it on Azure, but you have like 200 credits for students, but I think it's not too expensive, but we can use Google Colab because it is a tutorial. So we're gonna, I hope you're gonna code with me, because I hate when you have a tutorial where someone just like show you the finished code and they're just like, oh, this, and this. Just in case we don't manage to do everything in 1.5 hours, because it's really short period of time. Here I have, you see, done 20 epochs, trained model to see what's going on. So maybe in the end we copy paste something, but maybe. Okay, let's go from the beginning. Let's see what we're gonna need. Import numpy as np. We're gonna work with some multidimensional arrays, so we're gonna need numpy as pandas as pd, because we're gonna use it to read CVS files. Import matplotlib.py plot as plt, because I want to show you in the end the actual image, the prediction, and the ground truth, the actual amount of leaves in a picture, in an image. Import time, and we can import date time, because I like to see how long the training takes. From sklearn.model selection, we're gonna import train test split. We're gonna mostly work with TensorFlow, but this sklearn train test split is the easiest to use, it's the most convenient, so we're gonna use that. We're gonna use TensorFlow as TF, and we're gonna also import TensorFlow add-ons as TFA, because it has some functions that we're gonna need. Then we're gonna import TensorFlow.keras.models import model. Then we're gonna go on the layers, and here we're gonna see what all the layers we're gonna need. Layers import input conv2d activation max pooling 2d Latin batch normalization, normalization, dense concatenate zero padding to the, and I think we're gonna need average pooling, global average pooling, yeah, global average pooling to D. Okay, so you already see some hints of the layers we're gonna use, and what's really good news is that we have everything implemented in TensorFlow, and that's why TensorFlow is one of my favorite libraries. You don't have to take care of implementing one of the layers, figuring out all the math behind, even though it's important to know all the math behind, but you don't have to take care of all of that always from the beginning. TensorFlow.keras.optimizers import, we're going to use Adam. Then from TensorFlow.keras callbacks, we're going to see why model checkpoint and early stopping is important. Okay, I think I'm gonna need here pip install TensorFlow add-ons. Let's do this. Let's run this just to check if we have any mistakes. I'm gonna add few cells. Okay, can you please share the link for data? Okay, so this is the link for data. You need to fill this questionnaire, and then you're gonna get data. Okay, zero padding to D, my mistake. Okay, let's see if we have everything we need. optimizers. Let's see. Okay, finally, it's good. So you need to fill this questionnaire, then you're gonna get the download link for the data, but you can follow pretty much a lot of the code even without data, and this is being recorded, so you can go back when you get the data. Okay, so because my data is on my Google Drive here, I put it here, I'd upload it here. I'm gonna connect from Google Colab to my Google Drive so that I can use it. And while we're here, you can see I have A1, A2, and A4 folders. A3, you're gonna probably get A3 with the download, but you can ignore it, or you can try it out how it works with A3 also. So let's, for example, open A2. Here you see that we have some images. For example, for one plant, we have the original image. For example, this one, where you see a pot and a plant. Then the next one would be with mask, like that's separating background from foreground, background and the plant itself. Then here you can see the leaves are separated. And here, I don't know how good can you see it, because the centers of leaves are just like pixel or a few pixels wide, but that is the data. And what's really important is that the data is annotated by professionals. So we know we have a really, really good data. I think I'm saying this again. You need to, you tried it. Julia, did you try the link? And my email has link to as empty folder. It shouldn't be, because plant phenotyping here, you can see it even here. Okay, you can try it from here, maybe. Check. Okay, because I downloaded from here. Right. Okay. Okay. Thank you. Thank you. Okay. Okay. Great. So let's go. So I need to connect my Google Drive, Google Colab, import drive, drive.mount content/drive. Okay, let's see. So when you run this cell, it should be something like this. Permit this notebook to access your Google Drive files, connect to Google, you connect to your app, you allow it, you're gonna get an email indicating this, and okay, 1/ here, I think that's it. So this is fixed for everything from google.colab, import drive mount /content/drive. Okay, that's good. So we connected Google Colab, this notebook, with my drive, so I can access everything on my disk. But for the sake of this tutorial, I only have things related to this tutorial. Among the others, this folder where I have data sets and model checkpoints, because we're going to need a folder for model checkpoints. So let's set up some parameters. For example, the first one can be data path. Don't forget the /content drive, my drive, /DSC Belgrade 2022 data sets / Belgrade. Let me just check the Belgrade 2020. Okay, that seems good. Then we're gonna have checkpoint hat, and this is gonna be content drive, my drive. Don't forget my drive in this string, because I once forgot, and you don't want to know what I Googled to figure out what's the problem. It seems ridiculous, but it takes a bunch amount of time. Model check points, and make sure that you actually have model checkpoints and data sets on your drive. You have to, like, after content drive, my drive, you have to have this structure of folders in your drive. So you may be gonna do something differently. Then we're gonna say input shape as a tuple. Be careful, as a tuple. We're gonna need this. We're gonna say image shape is gonna be equal to as a list. Be careful, it's a list. 512 times 512. We're gonna go with batch size equal maybe 4. I'm gonna explain in detail when we get to the batch size how you choose it, why did we choose 4, and things like that. Num threads, let's be it 4. We need epochs. Let's go with 3. I know it's ridiculously low, but just for the sake of this tutorial, we're gonna go with really low learning rate, and I'm gonna show you what I got when I was running it really for a longer periods of time. But patience is gonna be, I don't know, 2. It's again small, but for the sake of tutorial, let's go with this. So how we're gonna represent our data? Okay, Julia, can you focus now on listening, and then you can obtain data, because again, it's a big data. I think it's gonna take not few hours, but few minutes, 20-30 minutes to download. Does that sound good? Because data is just to prove what we're talking about. I just want to explain you today what are convolutional neural networks and why they are important. Okay, Julia, you can write in a chat maybe. Do you want me to go slower or slower maybe? Okay, organizers, can we get maybe chat? Because I think that's better way of interacting. Okay, thanks, Julia. Okay, so these are some parameters. So what do we want to do here, actually? We're going to present our images as tensors, and tensors are like multidimensional arrays. It's really good to use tensors, especially when you work with images, because, for example, let's pretend this is an image. It has width, it has height, but also if it's color image, you have red, green, and blue part of the image. So it's like a depth of 3. So tensors are used in machine learning, and really, really important in machine learning for encoding multidimensional data. And we also have some libraries who work really good with multidimensional data in Python. So it makes total sense to use to present images as 3D tensors. For a start, let's write few TensorFlow functions that we're going to use. For start, I'm going to use this decorator. And what does this decorator says actually? It says that this is provided by TensorFlow and converts regular Python code to callable TensorFlow graph functions. You can search a little bit what are the graph functions and how the TensorFlow actually is implemented, but this is this has a better performances and is actually Python independent. So the first one would be get images and counts. We're going to provide image path count. So this is just like a regular function. It has this def, it has a name, it has parameters. And here we do something with this image. First, we're going to get image path. So it's going to be string. And these images are the PNG. So we're going to transfer that to something that can be held in memory, like a tensor. So we're going to go with the code PNG, TensorFlow EO read file, image paths, image path. And here we're going to say channels is equal to 3 because we want to have red, green, blue colors. So this here is going to give us the return. The image actually is going to be the shape size of the image, comma 3, because it has 3 colors, as I've already said, and the data is going to be integers. So before resizing, and why are we doing resizing? Because we have in our data sets different sizes of images, and we need them to be the same. So why did I decide to be 512? I was just going with something that works for my input in a neural network, in a convolutional neural network, and maybe it's like it's close enough to this one, and this one it's maybe far a little bit further than this one, but it should work pretty good. So you can try out with some other dimensions. You can maybe try 256, that's half of this, but just remember to change it here and change it here. So that's why we have parameters, because if you want to try out your convolutional neural network when you have with different image dimensions, you just change it on 2 places. So here I'm gonna say image. We said that image now is contained of integers, but we want this to convert image D type to what? Image TF float 32. In short, if we don't do this, we are probably gonna have some loss of data or some images that don't correspond to the input images. So this resize works with float. So that's why we are doing this. And now we're gonna return, we're using here image shape, that's a list, return image and count. Now you're probably asking, why are you like, let's see here, count. Why are you using count as parameter and then returning it? You're gonna see how we're gonna use these functions. We're gonna use it as a map on data set. So it's easier to implement it like this. The next function is gonna be for data augmentation function. Why is this data augmentation really, really important? And this is like a saver when you have a small data set, whatever that small data set mean, because you can do certain transformations on your image, and you can hold the original image. You can take the image that was, I don't know, rotated for 90 degrees. You can take an image that was like flipped, like mirroring image, and things like that, many other things. So data augmentation is really good when you have small amount of data. And the second reason why it's really good, because you don't want, for example, let's again use the example of faces. You don't want to your neural network to learn only faces that are like like this straight. What if someone is upside down or on the side or in some weird angle or just like a part of the face and things like that? So if we don't have enough different data in our data set, we can, with data augmentation, change a little bit images, transform them to so that we can have like a broader set of data. So we're gonna define data augmentation, image count. Again, I'm passing count because we're gonna need it. I'm gonna generate here one random number is equal tf random dot uniform. I think you already know what does this do. A uniform distribution. We're gonna get shape. We need to define shape like this. We need to say min val is gonna be 1, max val is gonna be 8, and d type is gonna be int 32, because we just want to get numbers 1, 2, 3, 4, 5, 7. Be careful, min val is included, max val is excluded from this. So we're gonna get one of the numbers, and what we're gonna do here, we're gonna say if df equal random number. So random number, because we obtain it like this, TF random uniform is gonna be like a tensor, small tensor. But if we wanna say if it's equal to 1, 2, 3, we need to say constant 1. So if it's equal to 1, what we're gonna do is we're gonna do a transformation of our image by rotating it. Rotate 90 the image. First need image, rotate it by 90 degrees, interpolation is equal rest. Nearest, I think I got it. Okay, so we're gonna do the same thing for 180 degrees and for 270 degrees. I'm just gonna copy paste because the code is mostly the same. Just be careful to change constant. 270. Okay, so those are our first 3 transformations. The next transformation can be mirroring. So again, I'm gonna copy paste to save some time. It's gonna be 4. Mirroring is part of the flipping, actually is part of TensorFlow, so we don't need TensorFlow add-ons. Here we're gonna say flip. Flip left, right. Are you gonna recognize it? Flip left, right. Okay, and we just need image, so we don't need this. Okay. If it's 5, we're gonna flip up, down. Flip up, down, and maybe one filter we're gonna use for 6. It's gonna be Gaussian filter. 2D. We're gonna need image, filter, shape, that's equal to 3, sigma, that's equal to 12, and padding, that's equal to symmetric. Okay, I don't have much time to go into details for Gaussian filter, but this is what it does. Like here you have maybe a little bit sharper image, and for sigma equal 2 you have a little bit blurred image. That's it. You can see what other things mean. Okay, no mistakes. I'm gonna need to return here, sorry, return image count. So why did we go all the way to 7? And here we have like transformations for only 6, because if the number is 7, we're just gonna go no transformation on that image. So the next part is actually getting the sets. So so sets are, okay, let's go to here. So A4 CVS file contains in the first column or in 0th column the names of the plants, the name of the plant images with extension. Be careful, it has this PNG, and the second column is actually the number of leaves that are contained in an image. Yeah, again, this is like expert annotation, so this should everything be really correct. For the sake of brevity, because I see we have less than 1 hour, let's go with only one set. Images A1 and counts A1. CVS path is data path plus A1 to get in the folder, A1 CSV to get to this file, and images and counts CSV is gonna be pandas read CSV, but we're gonna have to add the name of the columns because there are no names of the columns. So we're just gonna say image name and count. So what are we doing here? We're gonna read through our CVS file and we're gonna put the exact full path of the image in images A1. So images A1 is gonna be equal, we're gonna go with 4 int row in images and count CVS iter rows, just to go through this data frame. Images A1 is gonna be appending data path. And what I'm doing here is I want to get a full path for this image, because I'm going to use this function here and it expects to have a full path. Maybe you could put it here like hard-coded, I don't know, this data path or things like that, but we can do it like this also. Plus row image name, the name of the image itself. And here we're going to go counts A1 append row count. Okay, so we got that. We don't need anything here else. You would add here A2 and A4. It's pretty straightforward. You can just copy paste this code. And just to check if we got everything right, let's check the len of images A1. 128, and here we have 128. So that's it. The next part is going to be actually us deciding what are going to be our data, because here ideally or when I was doing on this project, I had A1, A2 and A4, and I just wanted to see like the performances of neural network when we train it only and use it for testing and validation. A1 set, only A1, only A4. I didn't use only A2 because it has only 28 images. It's pretty small, but then I mixed A1, A2, A1, A4, and I also had one set, one additional set from a company. So it was interesting to see how well it works all together. So here we're gonna set images equal to images A1, images A1, and counts equal to counts A1. Again, maybe this is not necessary because we have only one folder, but in case you have many more and you want to see what kind of combination works best, this is how you would do it. So now, first we're gonna separate our data into training, validation, and testing. You probably heard about training and testing data, but also we're going to use validation data set here. And it is usually used to provide an unbiased evaluation of model fitted on a training data set while tuning model hyperparameters. So you're going to see how many, we have a lot of parameters. We have even more parameters. So anything that can like check us if the model is progressing, it's good. So what we're going to use, train test split. Remaining, like x remaining, epsilon remaining, train test split. What kind of ratio we're going to use? We're going to use ratio 80% for training, 10% for testing, and 10% for validation. So also this is something that's discussing how much should you use for training, how much for testing, how much for validation. But let's try it like this and see if this works, because this is what usually is used. Random state, we're going to go to 8. I need to shuffle. We're going to say true. Test size is going to be 0.20. So the remaining is going to be 20%, and X training is going to get 80%. Now we're going to say X test, X val, like validation. Again, we're using test, train test split. X remaining, epsilon remaining, random state is equal whatever you want, shuffle true. And here I'm going to say test size is going to be 0.5. 50% of the remaining 20%, that's 10%. Okay, so we got this. We're using 2 times train test split because there's no implementation. Now that I know that's gonna split the data into, I know, 3, 4 or more sets, but this works pretty fine. Okay, so let's go on train data set. What we're gonna do next is that we're gonna use create tensor from our data, because until up now we had list and we were separating this list. So xtrain, xtest, etc. are lists, but we want to get a tensors. tf data dot data set dot from tensor slices. Okay, let me just clear one thing here. I had the problems with the naming of this function because it was like from tensor slices. It's like the input, the parameters are tensor slices, and actually what I need is to get tensor slices. So maybe I find it even online, someone said like maybe the better name would be 2 tensor slices, because you're getting tensor with this here, what we're gonna say, and that is x train, epsilon train. So it's like 2 tensor slices. We're also gonna use opportunity here to shuffle our data. Why? Because sometimes maybe the data is listed in ascending order of number of leaves or whatever it can be, and that's not good. So we need to shuffle it to change the order of the data, and we can do that here. Train data set dot shuffle len x train, just to make sure it shuffle it all the way through. And I'm gonna say reshuffle each iteration is equal to true. Reshuffle, it's written with 2f, reshuffle each iteration true. Okay, so we're gonna do pretty much the same thing for validation data set. tf data set dot from tensor slices x val epsilon val We can shuffle this also. So 1, 2, 3, shuffle each direction, true. True, okay. And test data set is gonna be equal to tf data dot data set from the tensor slices x test epsilon test. Okay, let's see how should we solve. Let's see if this works. From tensor slices, it's plural. Okay, this works, great. So for now, just be careful. For now, even in our tensors, we have strings. We have strings and integer numbers. What we're gonna do now is finally get image as an image. So for now, we had image as a string. That's okay, that's good, because we did something, train test split works faster on strings, but now we're gonna need to transfer these images into tensors, and tensors are gonna be width and height of the image plus and the third dimension is gonna be 3 because of the depth. Sorry. So now what we're gonna do is say train data set is equal to train data set dot map. Map is used for transforming items in a data set, and we have data sets. What's really good here is, because we don't have much time, but always check the type. Always check the type of X train, check the type of validation data set, etc., etc. We're going to use here get images and counts. So we're going to say get images and counts, num parallel calls is equal num threads, and we're gonna again map it, this time data augmentation function, because after we obtain the images, we want to do some kind of data augmentation on those images. I'm just gonna copy paste this num parallel calls. And we're gonna do the same thing for validation data set is equal validation data set dot. We're not gonna need this data augmentation here. And we're gonna also do the same thing on test data set is equal test data set dot map. So here, I repeat, before this, as in images, we had strings that were paths to the image. Now we're finally getting the image, decoding PNG and converting it and resizing it to this 512 times 512. After we've done this, let's see if we have any problems here. Let's see TF flip left, right. Flip left, right. See again. Flip. It should have flip left, right. It's not right, left. It's left, right. Just for the sake, let's write pass. Let's actually comment it out, because I'm pretty sure this is correct. Let's see if this works now. Oh, sorry, we have to run the cell. Okay, let's go. TFA, here is TFA, that's what I know. Okay, let's run it again, fingers crossed. Okay, let's comment it out because we're using precious times. Some things that are maybe not the focus of today's tutorial. I'm gonna figure out everything and I will provide you the code just in case we, and some maybe additional code just in case we don't manage to do everything today. So we transferred our images to actual images in data. So now what we're gonna use, what we're gonna do, usually when, okay, thanks support. Oh, Philip, okay, thank you, Nanad, so much, thank you. I wouldn't figure out, those are some sneaky permutations of letters, thank you. So that was the problem, thank you, Nanad. So now what we're gonna do, now our neural network would work like having image one by one. So you have whatever that neural network would be. We still didn't show the architecture. We still didn't write any code, but it would go one image, and let's say it's a black box. One image, after that image is done, the output would be some number, whatever, the number presenting the number of leaves, then it would go the second image. But why go one by one image when we can go few images in parallel? So that's a really good question. How much images in parallel? That's going to be defined with our batch size. And this batch size, sometimes usually you have to be really careful when deciding how big the batch size is, because sometimes it depends on your resources, and also sometimes I get an error saying that it's expecting that so many batches and I don't have that many batches. So, but usually if you get error like that, it's going to be self-explanatory what you actually need to do. So we're going to go with batching some number of images so that it can go in parallel. And we're also going to go with prefetching, like while the network is working on something, we're going to prepare the next set of the image. This is all like working some things in parallel is going to affect our training time. There's like really no general rule of thumb to which batch size works out best, but what was good for me is just to start with number two. I know that some tutorials are saying maybe bigger, but usually when I'm developing something, I'm trying on maybe even on my machine or on Google Colab, so that's all that it can handle, maybe 2, 4, and so on. So here we're gonna say train data set is equal to train data set dot batch size prefetch, let's say 5. This means it's gonna prefetch 5 batches, each batch size element. So each is gonna be 4 images. While data set is gonna be equal to, the same thing goes here. Test data set is equal to, oopsie. And we're gonna do the same, prefetch. Okay. We run this. Okay, now the most interesting part and the most important part is this. Let's figure out what this convolutional neural network is and how it operates. For this example, I've chosen ResNet. It is a little bit complicated, but what the good news is, once you figure out ResNet, the other neural networks, convolutional neural networks are going to be, let's say, easier. Of course, you're going to figure out that the architecture of the network, you can probably after this example, you can come up with few examples of your own. So the most important thing is to actually figure out the architecture of the network. Once we figure out what's going on here, it's really easy to code that in Python. Thanks to, you've already seen, we said TensorFlow keras layers and imported many layers, and that's going to be great for us. But first, we're going to need to figure out the network of the architecture of our network. Before that, I just want to go briefly over convolution operation, and how I like to study things is just like maybe you can work on convolutional neural networks and never figure out what convolution operation is. You can say, okay, it's like a black box, it does something, but I like to have even that math background of why is something working, how is it working. I think you're gonna need it, especially when you have input of one size and probably changed output. So for example, here, let's go to the simplest example that I could find. Here we have 5 times 5. Let's say this is one really simple image representing, it doesn't matter even what is it representing. In convolution operation, we have few parameters. One of the important parameters is kernel size. Kernel size is saying how big do you want your matrix that is going over an image. You see here how these numbers have like indices and it's a little bit darker blue. That's that kernel size. And this kernel, the numbers in this kernel, it's like a way of multiplying, dot multiplication of matrix, kernel matrix, and submatrix of our input image. And you're going over the image how many times you can. We're going to talk about that also. And you're producing also a matrix. So how this works? For example, here someone already decided that kernel size is 3 by 3 and that the kernel numbers are 0, 1, 2, 2, 2, 0, 0, 0, 1, 2. So when we go like 3 times 0 plus 3 times 1, 2 times 2, etc. 2 times 2, we get 12. So the next parameter that is defining convolution operation is called strides. Strides mean how much am I moving, how many steps am I moving to the right and down, like when you're going over the matrix. So here, if strides are 1 by 1, the kernel will be over this submatrix, then the next step would be over this. And when it's here, it produces 12. When it's here, it produces 17. And then it goes from here like this. If the stride was like 2 steps to the left and one step down, it would go this and this here. So it wouldn't have this matrix here, matrix multiplication, result of matrix multiplication. So you can see if we don't add padding, and padding is just like adding zeros around our matrix, we get smaller matrix. So that's really important when you're trying to figure out what the shape of your output of one layer is and how you're inputting in the next layer. Because a few times I happen to, maybe something was miscalculated or I wasn't paying much attention. I got to the point where I was trying, maybe on matrix 2 times 2, I had a kernel size 5 times 5. So it's like, what should I do? The computers, what should I do? How should I work with this? So don't go like in a minus or smaller than the kernel size, except if you're adding padding. So that's a different. So that's this famous convolution operation. And remember when I said that the convolutional neural networks are inspired by biological brain. This is actually how our brain works. It looks at the neighboring pixels and trying to figure out something there. What you also can search for is kernels for recognizing horizontal horizontal lines, kernels for recognizing vertical lines, and so on, because those are really well known. But what do you need to recognize that, like, there's a horizontal line in an image? So that's the famous convolution operation. Nothing, I don't know, special, fancy, just like a lot of dot matrix multiplication is going on here. And here you have one link that's a really good, like literally how the heading goes, intuitively understanding convolutions for deep learning. So you have even animations for this convolution operation. Okay, so that's convolution operation. We figure out what that is. So let's figure out the architecture of our ResNet, actually a little bit modified ResNet. First, we have input. Input is going to be our training. Input is going to be one of our, for example, let's go with only one image. It's going to be one image. 512 times 512, the depth is 3. So what is the next thing that we're going to do? We're going to add 0 padding. I think it's going to be 3. 3 is enough. That means adding 3. Can you see? Okay, you can see me. 3 zeros around the whole matrix. So the size is going to be 512 plus 3 is going to be 518 times 518. So this then goes into stage 1, where we have convolution, batch normalization, then ReLU activation function. Then we have stage 2. And in stage 2, things get interesting. We have max pooling. Max pooling is nothing like hard or fancy. It just looks at a certain area of matrix and gets the maximum value. But here we have something called convolution block and identity block. So convolution block is shown here and identity block is shown here. Let's first figure out what the convolution block is. Sorry, then we can go on the identity block because it's simplification of convolution block. So convolution block says, give me the input X, then transform it to 1, 2, 3 convolutions and batch normalization and ReLU activation functions. Then like concatenate that with input that's been only transformed by 1 convolution. And then all of that, when you like concatenate that in a certain way, I'm gonna explain you how you concatenate it. Also, go to ReLU activation function, get that through the ReLU activation function. So this here is what happens here. So for the sake of brevity, it's easier to show it like this. And the identity block is same as convolution block, just this input goes like pure without any transformation to be concatenated with this transformed output of these 3 convolutions. So something is happening here. We're getting input a little bit transformed and a lot more transformed, and then we're concatenating those 2 informations together. You can look at it like that. And concatenating informations, because maybe those transformations, this convolution is gonna affect the input in some way that certain characteristic important features is gonna be lost. So we have to like do this. We have identity block, we have convolution block. So stage 3, stage 4, and stage 5 are really similar. Their only difference is in the number of identity blocks and in some parameters, but we're gonna see parameters. Don't worry about that now. And in the end, we have average pool, flattening, like putting all instead of matrix, just like one really long array, and then we're going to have few fully connected layers. Okay, so let's write code for this. First, we're going to write code for identity block. The parameters are input, kernel size. This is the kernel size for convolution operation, and we're going to have filter 1, filter 2, and filter 3. Okay, that's it. Why filter 1, 2, 3? because we have here, here, and here convolutions. Conv1 is equal conv2d. And the documentation on the TensorFlow official site is like your best friend when you're working with this. You have conv2d, and it says like it expects filters and kernel size. You don't have to provide anything else. The padding is valid. The strides is 1 by 1 if you don't write anything else. What's really interesting and what I would like you to try out is convolution 3D. I know we're just like learning 2D, and I know that lots of people are like, okay, 2D, 3D, the geometry, the going from 2D geometry to 3D geometry is a little bit hard, but really when you figure out everything you need to know with 2D transformations, go to 3D. It is hard, I'm not gonna lie, because you constantly have to think what's going on now on a 3-dimensional level. So here we're gonna save conv 2D filter 1. This size here is already the resident has filter kernel size here 1 by 1. So we're gonna do that. Here we have input. Then the next thing is batch normalization. Batch normalization of the conv1. Then we have conv activation. Conv1. So you're probably asking yourself, like, what activation function should I use, or what kernel size should I use? And that's like a separate tutorial, separate lecture on itself. There are some really good scientific papers describing like what is when the best activation function and what is the best like kernel size. So I wouldn't go too further into that, especially because we don't have much time. So for the sake of going a little bit faster, I'm going to copy paste this. So here we have conv2, conv2, conv2. We're just going to go here, conv2, and be careful. In the second convolution operation, we're going to say that we're going to use kernel size. That is our parameter for this function. And we're going to say padding is equal same. When we say padding is equal the same, this is not going to happen. What happened here, like from 5 to 5, we got 3 times 3 matrix. So this is input, this matrix 5 times 5, and this 3 times 3 is the output. But if we say padding is the same, it's going to add enough zeros around so that if the input is x times x, and the output also is going to be x times x. So we're going to change everything. Okay, we're going to see here conv3. Okay. This is conv1, just be careful to change it everywhere. Conv2, conv3, conv3. Okay, I think we did everything. We just need to do now like this connection here, this connection. Input, concatenate on the output of these 3 convolutions. So we're gonna say conv3 is equal concatenate conv3 input axis is equal to 3. So what's happening here? So I'm going to use these papers because I think they're going to be easier for me to explain it. So let's first decide, figure out what is this feature map. Maybe that's better. So here on the first image of convolutional neural networks, we said like convolution, you see like from one image, we got 6 images. These are called feature maps. So you can think about like from one image, maybe that's RGB image, but we got more than one image. You can say, okay, this feature maps takes care of horizontal edges. This feature map takes care of of horizontal, this about vertical. Maybe this one is recognizing some part of the circle in a certain area of the image, this one in some other certain area of the image. So you have like more feature maps, and each and every one of the feature map is tasked with recognizing some part of the image and something in image. So either it be horizontal or vertical image. And here, we already written, like we have 3 convolution, and we have something like this. So these are feature maps that we got. And what we're now gonna do is say, okay, I wanna output those feature maps from this function, but I also want you to concatenate the input. So, okay, this background removal is not really good with these notes. So here we're adding input and we're concatenating. So we're adding, let's say we had like 400 feature maps and the input was, I don't know, 20, just for example. So overall, we have 420 feature maps, and that's going to be our output. So the output size of the size of the output is going to be height of the width of the image, height of the image, comma 420. So all of those feature maps. So that's happening here. That's really important to understand, because sometimes this moment, like from getting from one image to like 6 images, 6 feature maps, whatever that is. And I'm repeating again, we're having here some kernel size. Kernel size is probably going to be 3 times 3. And here we have 1 by 1. And here we have to figure out 1 parameter for this convolutional neural network. And here, if kernel size is 3 times 3, we need to figure out 9 parameters, because we need to figure out what are the numbers contained in a kernel. Okay, so when we have concatenated, we need to output is equal to activation relu as before, and just pass the conv3 relu, okay, like this, return output. Okay, so that's our identity block. That's what's happening here. And for the convolution layer, for example, let's I've prepared this feature map because I think it's the best representation of what's happening. We have an input image, a dog, and it's going through some, so this is kernel size. You can see these are different kernels. And here you have like maybe the edges are sharpened. Maybe here our edges sharpen a little bit on a different way. This has like a little bit of blurring, and this is like black and white image. So a lot of things are happening, and it's science itself to figure out what's happening actually inside the convolutional neural network. So that's a study on its own. So the next thing that we're going to do is we're going to define a convolution block. I'm going to copy paste the code for identity block. We're just going to call it conv block. And here, besides kernel size filter 1, 2, 3, we're gonna have also strides. So in the identity block, we use the default strides, and that is 1 by 1, moving just one step to the right, 1 step down. But here the default is gonna be 2 times 2, wherever we're gonna use it, and you can pass whatever you want. So convolution 1 is gonna be the same. We're just gonna add strides is equal strides. Padding same, okay, and here we're gonna add strides is equal to strides. Okay, and remember, we also need to do this convolution here. So usually this is called shortcut in a ResNet shortcut, so we're gonna call it the same way. Let me just not, okay, after conv 3 doesn't go through activation. Okay, this is mistake here. Conv3 doesn't go through activation on its own. First, it's gonna need concatenate input, then it's go through concatenation. Okay, so here we're gonna have shortcut is equal to conv2d. Filter 3 is gonna be used. The kernel size is 1 by 1 and strides is equal to strides. You can play around with these parameters, see if you change maybe here 2 times 2, how this is gonna change. First of all, the number of parameters is gonna increase by a lot, I would say, but you can just like play around to see if maybe you can find some better way of better perform the neural network with better performances. Shortcut, we're gonna do batch normalization here. Batch normalization on a shortcut. And here we're gonna say, okay, I don't need this, is equal and batch normalization shortcut, and the output, we're gonna say this is output, is gonna be concatenate conv3 and shortcut, not the input, because we need to transform input a little bit in convolutional block. I think that's it. Let's just not forget here this. Okay, I think that's it. So now when we defined convolution block, we can define the whole architecture of the neural network. So let's go. Now it's like really easy. We just need to follow this. But I still have something here to tell you, something important that was really that was like blocking me from understanding. So input is gonna be input, shape is gonna be input shape, and then we go output is equal to, the first layer is 0 padding, so we're gonna go 0 padding to the padding is equal to 3. Oops. Okay. To the padding is equal to 3, and we have input here. Then we go, I'm gonna write in a comment stage 1. The stage 1 consists of convolution, batch normalization, and ReLU. That's something that we have already written here. So we already know what to do. So output is gonna be conv2d. So the number of filters or the feature map is gonna be 64. The kernel size is gonna be 7 times 7, and strides is gonna be times 2 times 2. Output. So you're probably asking, how did you come up with these numbers? I didn't come up, it's part of the one of the recent implementations. There's a really good paper describing like and showing the performances of what is the best kernel size, and it goes like from 1 times 1 to 3, 5, 7, 11, and I think even goes to 13, 17, and 19. So to see what is like the best performance, but again, for a specific example. Output is equal to batch normalization. I'm just gonna ask the organizers, is it okay if we just use maybe 10 minutes after 6, because I wanna finish this example, like this is the most important thing. Batch normalization, output is equal activation, ReLU again, output. Okay, that's stage 1. Stage 2 is max pooling, convolution block followed by two identity blocks. So we're just going to use our implementation of convolution and identity block. And at the beginning, it's going to have max pooling. And max pooling is just figuring out in a submatrix of 3 times 3, what is the biggest value. Max pooling, link 2D. Let's not forget 2D. We're gonna use 3 times 3 submatrix. Strides are gonna be 2 times 2. Padding, it's gonna be same. We don't want to change the size. Output is gonna be conv block. So output is input for this conv block, and we're gonna say kernel size is 3. We're gonna use filter 1 is 64, filter 2 is 64, and filter 3 is gonna be 256. Again, this data is used from the implementation of convolution function, and because we have two same sorry, this is identity block. I went to identity block. We're gonna say identity block, it's gonna have the same values for filters. We're just gonna need identity block. And again, we're gonna copy paste this because here you can see we have two identity blocks. Okay, that's stage 2 done. Stage 3, it's gonna be similar. So let's copy paste convolution and identity block, and we need 3 identity blocks. We're gonna change the number of parameters a little bit. So here the parameter is gonna be 128, and here you can guess 512. Okay, I'm copy pasting identity block 3 times because the stage has 3 times identity block. So the stage 4, you can see how simple it is to define an architecture after we done the analysis, after we figure out how the network should look like, and after we separately defined identity and convolution block. So here, what are the numbers? 256, and here it's gonna be 124. So the kernel size is constantly 3 with exception of here, but you can play around, and that's the best way to learn, like change something, see how is it going, and so on and so on. So here we have 5 identity blocks. So we're gonna do 1, 2, 3, 4, 5. Okay. Stage 5, we're gonna copy paste this. Stage 5 is gonna be 512, 248, and we have 2 identity blocks. So copy paste. Okay. So now we've done all of this. We came to average pooling, flatten, and fully connected layer. So now we're gonna say output is equal to global averaging, average pooling. The output. After that, we're gonna have our output flatten output. And here, well, you can also play around with this. You can figure out what kind of dense layers do you want, how many nodes should they have, but I've used this one, 124, with the activation ReLU, as you could guess. Output output is equal to, and one more dense layer, 512 activation is equal to ReLU, and the output is as parameter, and one more dense layer with only one node because we wanted to have an output of just one number output. Okay, so finally, model is equal to model, inputs is equal to input. Remember that we defined it here, input, and outputs is equal to output. And finally, your best friend, model.summary. Okay, let's see if we have any mistakes. Okay, so this is output. Let's see what we did wrong, So maybe this is the best error that we could get. So be careful, like we have an concatenate layer requires input matching shapes so that it doesn't know how to concatenate these two, because here you have dimension 32 times 32, and here the dimensions of feature maps is 64 times 64. Here we have 64 feature maps that are 32 by 32, and here we have 256 of feature maps that are 64 times 64. And okay, here we have, okay, what could be the mistake? So something in convolution block is not working as it should, because we're passing input. I think these strides here are a little bit not necessary. Yeah, probably strides just divide by 2. Okay, let's try this out. Okay. Okay, great. So you have to be careful because we had strides here, 2 times 2. What was happening? The input was 64 times 64. But if you use strides, and you can imagine here, if we were moving two steps to the left, 2 steps to the right, sorry, we wouldn't have like 3 values, 3 columns, we would have only 2 columns. So that's really, you have to really understand how dimensions are. Let's see, Nana, I think they're using, oh, yeah, you're right. 3, yeah, you're right. Let's run this again. Thanks, Nana. And here also. Then let's run it again. So you have to be careful how you define the strides. By default, they're 1 times 1, and how they are changing dimensions of the feature maps. Because if you want to concatenate, as you've seen, feature maps that are just not the correct dimensions in the height and width of the feature map, the third or the fourth dimension doesn't have to be the same. It's just saying how many feature maps is there, and we're saying here concatenate by axis equal 3. Okay, so maybe a few more things I just want to tell you. Be really careful with the shape of the data. So maybe, let's see, for example, print output.shape is really your really good friend. So here in summary, you have most of the shapes, and it's really detailed. So it's important to somehow understand this and become familiar. I know it looks overwhelming because there's so many informations, but here you have like the layer type and the name of the layer, output shape, the shape of the output, because the output of this layer is going to be the input to the next layer. As you see, here you see connected to what? To input 400 to this layer. And also you can see here the parameters. So for example, the input layer 0, 0 padding has 0 parameters. And here we have 9,472 parameters. Let me just quickly explain why do we have here so many parameters. So let's bring out the calculator. So this is the first convolution. It has 64 feature maps. It produces 64 feature maps, and it is 7 by 7. So you have 49 numbers in a matrix, and you have like 64 of those matrices. But when you go 49 times 64, it just gets to 3,000, a little bit over 3,000. What's important here, like the formula is the size of the feature map currently times number of feature map from the previous layer. So why do we multiply it by 3? Because we have three feature map: red, green, and blue. Those are different feature maps because the depth of our input data is actually 3. So for the red one, we're gonna have 64. For the green one, 64, and for the blue one, 64. That's why we go 7 by 7 times 3. And then we go is equal to something, 147 plus 1, the bias term. The bias term, like in most of the machine learning. And then we go this multiply by 64. And then we get this number here, 9,472. You can go over other parameters to figure out how many is it. Here, let me just scroll down to the dense layers. Okay, dense layers. So why do we have here like this much parameters? So we have here 1,024. So let's get a sense. 8,308,962 divided by, it has in the previous layer 8,192 plus 1 bias times 124, because you have these are fully connected layers. You have to connect each neuron from the previous layer to each neuron in the next layer. So in total, we have over 58, almost 59 million parameters. So that's huge. That's like huge. And let's do some kind of sanity check. Like we have over almost 59 million parameters, and in total we could have how much of our images? Like we can have 600, less than 1,000 images. The good question to ask is this number of images enough to determine these parameters? Because otherwise it doesn't matter. Like you can train it for a really, really long time, but if you don't have enough data, then it's just gonna produce something, but is the data going to be really correct and it's going to be like generalized? That's a really good question. So because we don't have much time, I'm just going to go into this code here to show you what else we needed to do. I'm going to share the code with organizers and the presentation so you can get this. Here we have model checkpoint. This is really important to do, like restore options when you're doing something that's really time consuming and that can like break any moment. So we want to save best only. So it's saving every time we get some model that has a better performance, it's going to be saved. Early stopping is a lifesaver because you don't know how many epochs do you want your model to be trained. Maybe it's 10 is enough, maybe 20 is enough, maybe 200 is enough. but you never know. And usually, as with many other parameters, it is done like empirically. You just figure out, okay, maybe this produce good enough performances. But with early stopping, you can say, okay, if for the patient's amount of epochs, nothing is happening, it's not improving, then stop it. You can say, I want to train for 1000 epochs, and you set patients to be 10. If nothing is happening from, for example, 100 to 110 epochs, nothing is getting better, the performances are not getting better, it's gonna stop. So here we have, I really like to see the time my training is taking. So here you can see the start time, the epochs, some information related to that, how many seconds have passed. This is like really important information, and when did it ended. After that, we have evaluation, and we also, what's really good with the checkpoint is that you can you can load model, the best model. Usually it saves the parameters, so you can say, okay, don't go from the beginning, load the best model and then continue training it maybe for 100 epochs to see what's going to happen. And here in the next part of the code, I just wanted to see what's going to happen, to see some images that have like the best value of predicted and some ground truth. So here you can see it predicted 2.567 leaves, 2.5 leaves, and the ground truth is 5. And look at the other predictions. 2.56, 2.55, 2.57, 2.58, etc. So everything is like 2.5. So something is not happening, something is not right. Probably the number of epochs should be changed. And here in presentation, after training for a lot of epochs, you can see some of the best results and some of the best results on some of the trickiest examples, because here, I don't know how good can you see, the image predicted is 8 and ground truth is 8, but you have overlapping, you have occlusion here on leaves, and even the small leaf here is just like peeking from beneath the bigger leaf. So it's really even hard for us as humans to count the leaves. And don't be like tricked. Sometimes it's not easy even for humans to count the leaves, especially the young leaves that are just forming. Like, when do I include you? How big you should be to be counted as a leaf? And on the left, on the right side, you see some plant that has, well, to say at least, a lot of things happening. See this leaf here, it's like this, and the image is taken like this. There's so much overlapping here going on. So you see here almost the complete occlusion, the complete overlapping, and because you're gonna get the presentation, I really would like you to try out to count the leaves manually. You as a human count leaves and see how many you can get, because predicted is 28 and ground truth is 26. And for the end, if you have any questions, I think you can ask now. Tech support, please correct me if not. I'm going to share with the organizers the code and this presentation. And please, if you have any questions, add me on LinkedIn or write me an email. I really would like to continue this discussion. I mean, this is the area and the whole data science that has so many things going on. And I think I said a few times, like with the kernel size, you can make, you can write a book about kernel size. You can write a book about epochs. Like the convolutional neural network is consistent of so many parts, and all of those parts are to some extent complicated. So I tried here to explain you the essence of convolutional neural network and how you can work with data with some real world example, because this plant phenotyping, for example, segmentation, leaf counting, and things like tracking leaves over time, for example, they are really necessary, and there are like whole laboratories working on that. So again, it is my pleasure. Yeah, okay. I'm gonna pass you this. I'm gonna pass you the done one, because it has more code. And this, let me just name DSC Belgrade 2022 ResNet, something like that. Okay, sent. And maybe here and here. Okay, I think I copy pasted good. Okay, thank you all, and please add me on LinkedIn, write me an email. I really would like to continue this discussion to talk about, I know, the most current scientific papers, and really good source of learning are papers and also conferences, because this is the area that is like hot right now. So many things are going on. Someone is constantly figuring out something new, and it just, you need to keep up with everything. Thank you, Helena. Thank you, Helena. Thank you, Julia. I'm sorry I didn't have much more time, because it was really short to put everything in just like 1.5 hours, and to be like a good experience, good learning experience for someone. Okay, thank you so much.
So thank you for an excellent tutorial. I hope you enjoyed, and thank you everyone for attending. So enjoy the rest of conference and tutorials.
Thank you. Bye.
Goodbye.